Hello, Energy Physics here with the National Drone Science series of lectures and documentary videos. We're going to create a series of model rocket and drone videos that I'll be posting to the web so that you can see some of the 97 different projects that I've been working on since about 2015 or so. And some of them are quite complicated, others are simple model rocket projects. I've got some automated rover and automated model rocket and automated vertical VT0L, VTOL vertical takeoff and landing quad plane projects that are going on. Very large one, as a matter of fact. And so we'll do these videos over a period of time to give you an idea of what Energy Physics is working on, both at the National Drone Science University lecture series and the National Space Science University lecture series. We're dividing them into two different conceptual frameworks for those who enjoy space compared to others who may just want to look at how to build drones and drone technology, CubeSats, robotics, things like that. So we're going to start this first presentation with a boost glider concept, as it's to me quite interesting. I'm a member of the National Association of Rocketry, and NARAM 63 is coming up, and there's a number of 6 different events, one of which is a boost glider contest. And this year, instead of boost gliding, they're distinguishing that with a rocket glider, where the only difference is what comes up has to also come down, and it can't separate at any point. So everything has to remain together in a rocket glider. Whereas a boost glider, you can use a boost pod that can separate from the main portion of the glider. So we're going to start this presentation slideshow from the beginning and walk through it relatively quickly. We started out with our first pod reusing an old, really old, probably 1975, 76. I believe it's one of the old Estes kits. It could be Centuri kit, and I just don't know what the name of it is because I can't find the exact kit anywhere anymore. But we're calling it the Nigel, and it's a boost glider pod. And we've been designing a number of flop wing type designs with thin carbon fiber booms in one shape, one line, so that we can 3D print a number of our components. And then we're going to fix up this Nigel rocket to be a portion of the boost pod and reuse it. Of course, we don't want to lose it because it's so old, so it's just going to be mainly for show. I won't go through the details, but every time I do a design, I walk through the basic specifications of each of the rockets, all the way down to getting center pressure and center gravity location from the beginning of the nose cone. I weigh each of the masses and keep detailed records on the designs and the systems for recovery. This particular Nigel had a repair history, obviously, had a damaged fin from way back, probably from just storage. An old style balls and nose cone. Yeah, amazingly, it had an engine clip at the time. And so we basically realized that over time, the old wood glue, the aliphatic glue, it's over 40 years old. We believe, like I said, it was a Centuri company kit. Originally painted black with red fins and white fin trim, but I can't find that old rocket in any pictures that I've got. So we're going to redesign it to be a pop pod boost glider and attached using the PLA printed release system. We'll also create, along with it, 13 millimeter tube variants in addition to this particular tube variant, which is a body tube 20, 18, 19 millimeter tube.
This model rocket, which I currently call Nigel, is in need of some repair for a damaged fin. We'll put some epoxy on it and a large round filler. It's a very old rocket that came from a long time back, and I need to try to figure out what the original model kit that it came from currently we call it Nigel because it has to do with some of the rocket altitude calculations that I did in 1972.
So the first thing we do in picking rocket glider parts and components, for the gliders themselves, we want them to be ultra lightweight, especially for any competition gliders. And balsa is such a high variability in mass that the density does matter. We want to find out of the hobby grain balsas, we want to locate the C grain types, which you see there on the left, which is taken through a certain portion of the wood fiber. The B grain and the A grain are less capable of strength, and they tend to warp a little bit more often just because of the way the grain is cross-cut. And you can see in the upper picture the C grain is cut from down through the center, the B grain is an offset, and the A grain is an offset, and how it's typically cut through the pith and center of the balsa tree. We want to get densities as low as possible, down to 5 to 7 pounds per cubic foot. The balsa is 6 to 20 pounds per cubic foot is above competition capability, but most of the grains that you're going to find in the store are like that. And here's a photo of Kitty. This is Dusty. He's been having constipation ever since he was a little kid. He's got a disease called Mager colon. So we leave him out and let him run around as much as possible, and then we have to very carefully manage his food and water intake. So I'm going to set him down so he doesn't walk across the computer. We love all of our cats. Got a lot of little rescues. So back to the balsa system. Again, we want to find the C grain, and we want it to be around 5 to 7 pounds per cubic foot. And we basically measure that in the store. We take a little gauge with us, a little weight scale, and use that to locate the lightest wood that the shop has. Then we go into OnShape, which is a online capability for modeling, and later we'll do some simulation in RockSim or Open Rocket, which is free. But we start off pretty much modeling so we can do 3D printing of parts. Convert this over to a slicer software, and then print that out into G-code for our 3D printer for CAD. We draw main boost glider pivot flops. This is a pivot device for the initial boost tube that goes in it, and then we flop the wings out. It's just one of the mechanisms we use to get wings set up. And they look something like this as they deployed. With the outer edges, they're flop wings. They're controlled by 0.15 inch piano wire that's cut at a C-type and then folded and taped and then glued with carbon fiber and epoxy. We've done several sizes, 14 millimeter swash plate and a 19 millimeter swash plate for these swing wings. And then 3D print some of the connections to the balsa. This is our little boost pop pod. Again, we're not exactly simulated the Nigel in this. It's one of our favorite designs, elliptical fins with small BT-20 or BT-13 body tubes. These are competition rockets that we like to build and have used and deployed to NARAM 62 contest. We don't do too bad. This is our larger glider, rocket glider wing pivot flops. Again, this is a boost glider because it's going to pop out at some point and recover. Once we've got the OnShape design, we export it to a stereolithography model, and we import that stereolithography into a 3D slicer app. In this case, we're using Ultimate Cura, but there's a number of tools out there you can use. And we print the nose cone, save the G code to a workspace directory and a micro SD card, And we put that micro SD card into our 3D printer, mount the drive, and then go through the print sequence. We can also CRC laser cut fins. CRC lasers are available at the universities that we have around the area here. And for that we need an AutoCAD.dxf format, which is typically used by the RDWorks version 8 import tool that we use to communicate the G-code to the CRC laser input cards. And show you how to do that later in a different lecture. This is the import of the RDWorks of a fin that we cut out, laser cut in the past. So we want to start out showing our designs for rocket boost gliders. Typically the contests are half A or A. In the NARM 62, NARM 63 will be an A rocket. Half A for NARM 62 recently. So you can see the results of that if you go to the website on the National Association of Rocketry, and then look up the NARM 62 events national meet. Our Pop Pod boost glider swing wing has that 25mm swash plate, and we basically want to create a number of different versions of this, large and small body tubes. So we tend to reuse a bunch of our small pieces of balsa. We're not ashamed of gluing pieces together and then putting cyanocleric glue or epoxy over top of them, and even a layer of carbon fiber or fiberglass to strengthen them. Depends on how much mass we want to tolerate. But we start this baseline out for a swing wing version, and the boost pod is with a little pod pylon attached to it.
The initial parts are ready to assemble for the rocket glider. It consists of a small 13mm tube, 100mm long, with a piece of basswood that'll be the swivel points for the wings, and two side attachments that'll hold the pylon standoff, and then of course we have a carbon fiber, 25mm section of fiber that'll serve as the main boom connecting the tail and the rudder to the pod and the wings. This will be a swing wing version that's activated when the pod reaches apogee.
And activation is done through a burn cord, by the way.
The nose section of the rocket glider is almost complete. The plate for the wings, sliding wings, is connected to a pylon, and that's connected to the carbon fiber boom. Carbon fiber boom is pinched in between two side plates, and that's attached as a pylon to the main 13mm engine tube. When it's finished, we'll have swing wings that swing up into position with rubber bands that are attached to the forward area of the nose cone, and they'll be released with a ejection charge pulling a pin that then allows the rubber band tension to swing the wings into position. The tail section is now attached to the rocket glider, and we'll just wait for it to dry. It's got a slight 1 to 2 degree up indicator on the elevator, and we'll be countering that basically with the swing wing. It should be nice and stable. The nose section of the rocket. Well, looks like the boost glider, the rocket glider that we built is ready. And we'll be sanding it down and ready for wings to be attached. Well, the balsa pattern's been cut for the boost glider sections, left and right wings, the stab section. Got two Whitcomb winglets that are going to run on the side, and one rudder. Cutouts have been made for a slightly smaller version of the previous boost glider. And so we'll have basically a high lift loft and a lower lift loft type boost glider platform. It'll have width and winglets also. So we've got a whole set of boost glider and helicopter kits that are ready to build. The larger airplane is about ready for assembly. Just need to go get some carbon fiber fuselage and nose cone and pop pod section built. The helicopter blades are ready to attach to the PLA printed helicopter heads, and we'll see how that works. The pods have been set for the initial platform sanding for the two boost gliders and the two helicopter gyrocopter contest rockets complete. Now the second task is to put an airfoil on each of these blades with a beveled sanding plane. And once we've completed that, then we'll end up doing the fine tuning on the sanding to fine grit. Sanding while it's easy, and then we'll dope it and smooth it and polish it later. The boost glider wings have been submitted into a dihedral shape and center fuselage assembly, which is basically a small 3mm carbon fiber strip. And the Watkins winglets have been installed upside down with the dihedral the opposite direction. The next step would be to install the stabilizer. Well, this has been a long-term project for the boost glider. That pop pod section has been completed, it's dried enough, and we've attached it to the nose cone, which basically is the weight and balance for the dihedral with width and winglets on it as a boost glider. It's large, wide, high aspect ratio on the fins and on the chord line for the wings. So we'll see. It's ready for weight and balance testing and glide testing. The initial platform. Okay, the rocket glider is almost ready for integration. I just need to add a nose cone and the swing wings on it. And while we're at it, we've actually got the capability, this is sort of a wild idea, of flying two of these at the same time. The pod section, basically for the upper boost glider, can be replaced, and in that same area I can put the rocket glider pod, just attach that to the nose cone, and now I've got one on top and one upside down on the bottom. That would be a swing wing. Basically the two rockets would go up and separate, and the only thing I have to figure out is how to get one of those to fly without the nose cone on it and detach at that point. So it'll be an interesting idea. We'll see what we can do with it. Okay. The boost pod for our boost glider is just about finished. The tail section fins are now attached, and when we're done, the glider, which is already built, there's two of them, will just simply slide on as a nose cone attachment, and that in itself will allow it to detach from the boost portion, and then it'll pull a streamer out as it goes and descend as two separate pieces. The boost glider competition allows the pod to come down separately. The rocket glider contest, which we are just about finished with here, that has to all come down in one piece. So the nose cone on this one will be fixed, and when it ejects, it'll simply activate the swing wing mechanism. The boost pod. This model rocket, which I currently call Nigel, is in need of some repair for a damaged fin. We'll put some epoxy on it and a large round filler. It's a very old rocket. It came from a long time back, and I need to try to figure out what the original model kit that it came from. Currently, we call it Nigel because it has to do with some of the rocket altitude calculations that I did in 1972. The Nigel glider pod booster that we've been using for a small glider launch assist has been repaired, and the glider attachment placed on the side of the rocket that'll match up to small boost gliders, and so we've given it a paint job and it's ready to fly. We pulled the old shock cord, which is a very, very weak elastic, and with an Estes triple fold attachment point, pulled it out of the old Centuri rocket nose cone body tube combination for the Nigel boost glider. It's necessary to do this because the shock cord is not going to last much longer, and we need to replace it with Kevlar, more modern connection, and an outside connection for NRC contest flying. This will be a boost glider capability that we'll try to be very careful with, because this is the oldest, last remaining rocket that we have from the 1975 collection of Centuri and Estes rockets. This model rocket, which I currently have, to remove the shock cord mount, just very carefully insert a small X-Acto knife and sort of twist in between the old glue and the body tube with some careful bending and twisting of the paper. It should just pop right off if the glue is old. The Kevlar shock cord has been mounted to the Nigel pop booster for our boost gliders, and we're about ready to load recovery wadding and some bulk barf into the tube, no more than about 1.5 times the diameter of the inner tube. Just have to be careful. This is an old rocket. We don't want to lose it. It's one of the original 1975 rockets still left from our Centuri purchase a very long time ago. The wing portions for the mini glider have been constructed. The small-scale boost glider stabilizer and rotor sections have been glued together now. Final assembly will be to put the slightly inclined stabilizer onto the carbon fiber fuselage. The wing portions. Smaller gliders are designed for these conventional rail and key assemblies with the small pop pod booster. We'll be putting a wire engine retaining clip on and fabricating the nose cone out of PLA, and then get the key and hook installed, and we'll test these smaller gliders.
So that's the end of the automated portion for the most part, but we had some glider airfoil data. Basically, in the contest, you have to take the time and care to create an NACA type airfoil for your glider, or it's just not going to get a lot of endurance time. You'll get less than 20 seconds of airtime if you don't do a really careful design of the airfoil shape. There's some numbers to think about in terms of aspect ratios and route distances, but just pretty much come up with your own design and just test that and iterate toward the best glider performance. The proof is in the actual flight. You can also use some charts that were created by Trip Barber, an MIT graduate who's also a member of my National Association of Rocketry local club, which is the Northern Virginia Novar Rocket Club. And we launch out at Great Meadows in Virginia once a month and have a monthly meeting that we have together to discuss various club issues and how we're going to support the high school kids in TARC competitions, things like that. But these charts will help with trying to determine your maximum coefficients of lift, your drag coefficients, and how to shape and optimize the various wing airfoils with their spans and aspect ratios as a function of lift. While we were at NARAM 62, we took some good photos of the successful boost glider types. Again, NARAM had a half A 13mm boost glider competition. So these are some of the basic designs that were presented, the trapezoidal being the most common wing shape. easiest to build, and then of course airfoiled. You've got an inverted trapezoid. It's also possible, which doesn't increase the lift any more or less, I believe. The angle to the wing angle is basically for high-speed aircraft, so you could actually have a straight wing and get just as much lift and possibly more at low speeds. And this is George Gasaway in the middle, a very famous National Association of Rocket member for many, many years. George has done a significant amount of design and testing contribution for the rocketing community. He's a great person to talk to, and he's just got a tremendous amount of knowledge. He tends to build elliptical models as his favorite wing platform, and I kind of agree. The elliptical airfoil, to me, has the least drag for the best performance, but you can test your own systems. Then there's the very popular, well, not so popular, but every now and then you'll see Delta version. This can come in a kit form, or you can build your own. I believe Apogee Components carries a kit version of this, and then of course you can just take a look at the design, put it into Onshape, and laser CRC cut your own balsa to these Delta variant components. Remember that there's many kits out there that have boost gliders. This is just one of ours that is surviving since 1972. We tend to be careful about these kits because they're worth a lot of money and no longer available. This is the Condor version of an Estes kit that has two boost gliders that pop off the side. Now we'll take a look at the rocket glider. Again, the only difference is that with a rocket glider, all the parts have to remain with the rocket, and nothing can separate. If it does, your entry is disqualified. Can't descend with a parachute or a streamer or anything. Everything, again, including the motor, can't be ejected. There's a number of these types of designs. One of our favorite is the slide wing, where the wing is mounted lower during launch phase, and as it reaches apogee, the wing is triggered by a rubber band and a burn thread to slide up to a wing stop. And there's a number of designs for that. And our favorite is actually add a flop wing to it, where the outboard portions of the wing and the dihedral basically flop outward using 0.015 piano wire as a flop wing spring. And these have to be attached with tape and fiberglass, keeping it lightweight. Second common type is a slide pod. Basically, you're just changing the center of gravity of the airplane, the glider portion. By in the boost phase, the slide pod is fully forward, and therefore the CG and center of lift and center of pressure is behind the center of gravity, which is what you want. And as the ejection charge goes out the front, it pushes the slide pod backwards, changing the center of gravity closer to the center of the wing. Chord line pretty much there, around 20% is what you're shooting for center of gravity location. Another common design that I believe George Gasaway produced a number of plans for is the auto elevator. The wing doesn't move, and you don't change the CG, you just change the angle of the elevator or canard. And again, that's done with a very lightweight piano wire and a thread that's attached to a burn thread and a rubber band. The spring itself, as the thread burns through, the spring is allowed to pop the elevator up, and when the thread is pulled through the little pivots, it holds the elevator down during the launch phase. Another really common version is the swing wing. It's not as competition savvy as the slide wing, and not as competition capable as the swing flop, which is a typical design used most often by Europeans and tends to have very high performance. But the swing wing itself can have two wings that pivot forward, but it does tend to be too heavy and complex to be highly competitive other than in the higher engine classes. And then the old style, Estes used to build, and Centauri used to build one rocket glider that had no moving parts, and the only problem was it's extremely difficult to trim these models so that they boost straight up and then transition to a glide without having any shifting of center of gravity. And it's a matter of boosting and canting the tail slightly, and you almost never get a successful straight boost. Quite often you can end up in a loop. The moving parts rocket glider is, again, old models, been around for a long time. Astron Falcon was one of the first, and this is again a 1970s design that is almost never flown anymore. There's other designs to the pods. Most of the time you're using a burn thread that runs through a small hole attached to a pin, or there's a vent hole that you pull the burn thread through. And you need to use very, very small threads, not the typical Estes type thread, but smaller than that, because you want something to burn through fairly quickly. The auto elevator design again uses that music wire spring detail, and it just holds the elevator up when the burn thread is released, and the burn thread is put through the pins there on the rudder when it's put into boost phase, and it holds the elevator flat. Slide wing, again, we like this design a lot, especially when you combine it with a wing flop. And it's again, rubber band gets attached to the leading edge of the wing that has a little carrier. Sometimes it's a square box that we 3D print. Sometimes it's a little slider rail. Just depends on the design and how you want to manage this, whether it's a carbon fiber boom or a wooden boom. And the rubber band is attached in a loop to the front pin up near the engine pod, and that runs back to the rubber band on the wing. This provides your sufficient forward movement and spring tension to get the wing all the way toward the front and slams into the little stop up there in the front. And that happens basically when you thread your burn thread from the little hook that's on the underside of the carrier, and that goes through a pin that's in the back and then loops forward up to another thread pin that allows it to angle over to the nose, and you put that through the little hole in the nose and tape that down. As the engine ejection charge goes out, it burns through that little thread and everything releases, and the rubber band pulls the wing forward at apogee. Just some details again in the design of the basic components of the slide wing. And there's a number of different plans out there that you can use. Tom Beach made this particular one quite some time ago. The B engine type slide wing rocket glider. And the slide pod, as we mentioned before, the pod slides back from a boost version, full forward CG, to a glide version where the CG is shifted back. Again, this is controlled by the burn thread that you see designed here. The swing wing we actually like a lot. It's a complex design, especially when you combine it with flop wing, dihedrals on the outside. But again, it tends to be heavy and complex, even though it's really awesome to watch it deploy. This is a drawing by George Gassaway in 2004. It can also use balls of pins, screws, or barrel bushings for these, or engine adapter rings to form bushings for your wings and pivots in a swing wing type of configuration. So you don't have to limit yourself to a single balls of pin or metal rod or pin type configuration. Key in rocket gliders is to make sure you always have airfoils on them. The more sophisticated the airfoil, the greater you're going to get competition lofting and competition times. If you can get it to glide for at least 1 minute, that's pretty competitive. Anything under 20 seconds is not. And the best way to sand the airfoils is to use a sanding block, and then sand from 80 to 120 grit, and then 180 to 220 for finer shapes, then 280 to 320, and then finish up with 400 grit paper. And leave the Leave the competition wings unpainted because it adds additional weight. You can use Japanese tissue or sailplane finishes. Um, Most people just use magic markers to color the bottom of the wing, tail surface, to show up against the sky. Use a red or orange marker to color the top surfaces and make it easier to see if it's fluorescent, red, magenta, or orange. There's the basic steps to building a rocket glider. We'll just walk through them real quickly. To do this, you'll need a hobby knife, some cayenne acrylic glue or epoxy, a ruler and a straight edge pencil pen, and 100, 224 and grit sandpaper is the minimum on a sanding block. Just mark and cut out the general parts list. You can also CRC laser print these from a one-shape design, which is what we typically do. And we've got stabilizer, rudder, pylon, which is typically cut out of basswood or plywood or carbon fiber. And then the base supports are done with basswood or hobby plywood. The boom is typically square wood or carbon fiber. We tend to prefer the carbon fiber rods, although they may be slightly heavier than the balsa versions. Cut out all the parts and sand all the wooden components before you're ready to begin the assembly. Then you basically step through the motor tube. We don't typically use these rod guides anymore. Most of the time we'll either put a rail button on there or we'll use flyaway rails, which are starting to become very popular. Flyaway rails were designed by Apogee Components, and we 3D print our own versions of those. And they just release with a rubber band. If you want to see those, you can look them up on some of my other videos. The third thing you do step basically is to mark and cut the stabilizer and the rudder. Attach them to the bottom of the boom upside down. Generally it won't fly conventionally if it's attached to the top of the boom, and they normally fly with the nose pod above the CG with the nose high and heavy. So it's a design concept to remember. The tail and stabilizer are typically inverted from a typical airplane. And then you want to work the rocket pivot, swing wing pivot. There's a number of different ways to do that and a number of different configurations that are used to create and initiate the swinging wing. Sand everything, mark and cut the holes and the hook locations for the wings, the flops, scissors, whatever. And go ahead and epoxy and put a little piece of carbon fiber or fiberglass over top of the areas if you want to use reinforcements. It's very popular to have an international rocket glider build. These are known as S4s. The contest is typically flown in 3 standard rounds, necessary 1 or 2 fly-off rounds. And there are certain restrictions on the typically A power class for both seniors and juniors. And the score is the sum of the duration of 3 flights, not just your 1 flight. So you're typically looking, 60-second flights each, and 180 flights for 3 of them. 180 seconds is fairly competitive. Although to really win these things, you're going to need to go over 2 minutes or so. 2, 3, 4 minutes is not uncommon if these gliders catch thermals. If you're looking for thermals to win these contests, which is another reason you may want to design an activated dethermalizer, because they can fly away from you and you have to return these models to score in the contest. We won't walk through the parts list, just to give you a real quick view of what goes into one of these S4 International Rocket Gliders, in this case a design known as a Switchblade from RJ Rockets, I think. And we'll walk quickly through that because it's unique to that particular kit. Estes has a flop transwing super boost glider for $89. It's a large kit. We don't have a picture of it yet, but we'll put one in there. And then there's a lot of kits for the easy slides, the slide type configuration, different sizes. There's the easy slide 1, 2, and 3, and basically just different size and different motor sizes, depending on what kind of contest you're going to enter. This is some pictures of them. The Bumblebee is a quarter A version, probably the smallest of those. And again, these come from a particular company. Notice that the frame boom sliders are PLA printed, and that's what we tend to build. We PLA print these center sliders and then epoxy them to the wing. Cirrus Breeze is an Apogee Components rocket glider. Again, this is designed by the owner of the company, and typically follow all these designs follow pretty much the same design principles. This is how the release and boost connection is done. His parts are CRC laser cut, also generally out of hobby grade plywood and balsa. Spanish International S4 is a very common design. In fact, it's one of our favorites. You get into swing boost glidings, you're going to make these wire hooks out of 0.015 piano wire. So go ahead and make a bunch of them up in a little plastic bag. Just keep them in storage for future builds. That's really the most time consuming. The rest of it's easy to cut out, but getting all those little wire hooks bent and cut with a little pair of wire cutters is tedious and takes some time, so do that first. This is a drawing of how you create that flop wing dihedral. It's basically you cut 0.015 piano wire. Initially it's cut into a C and bent into a C where they both face the same direction, and then they get the spring effect. You twist one of them so the pins are opposite to each other, and you tape that down with Tyvek tape and thread that's run through. That's a thread that's run through to hold those pins in place through the balsa, and then you epoxy that down. You can even put a small piece of carbon fiber just to stiffen that up and reinforce it if you need to. This is a complicated version of the swing flop, and basically it's a pivot flop, a Russian design. It's called Russian wrong. Sorry about that, Russian. Didn't mean to do that. RUSSAIN. It should be Russian pivot flop. And Europeans are the first to invent these pivot type wings. Initially it was just a pivot only, and then they created the flop version of that, and allows a much longer wing surface to be used. Notice it has a dethermalizer on it, and then the rubber bands, of course, create the spring tension necessary to swing the pivot. RJ, I think Designs has got probably one of the coolest designs we've seen, also the most complicated. It's based on the Interceptor 2 version, which actually was first done in World War II as a means of getting target practice. So he's gone and looked at those old style designs and made some modifications to come up with a modern version of this Interceptor 1, which he's calling the Interceptor 2. It's a nice design. Again, too complex and heavy for doing really well at competitions. The swing flops tend to do better, and the slide flops tend to be the best, in my opinion, for competition. Less weight, less complexity in the design. J&H is the guy that builds a number of these different models. He's even got radio-controlled versions of it if you really want to get into controlling these with servo and transmitter transceivers, just like you control your rockets or your airplanes or your drones. So the technology is there to have these small servos inserted and used on these very lightweight gliders, rocket gliders. A close-up of the Swivel Pivot, which is a version of the swing wing. Instead of having two pins, it's got one, and the wings overlap. Jim Walker's original Interceptor, really cool design, but World War II, and it actually was patented in 1939. So this mechanism is very unique and quite sophisticated, and he manufactured these for a long time and then sold them for a long time, and kids everywhere had interceptors that they would launch with rubber bands. You know, you can see that whole mechanism pivots the wing and it slides backwards, and you launch it with a rubber band launcher. Pretty sophisticated. Different, more modern versions of it. And Joshua Finn is the guy that has duplicated this design. Doesn't have any plans, just see the A.J. Walker patent that I just showed you. Stiletto is another version. It's a D-slide wing. Again, a lot of model rockets have these various design plans. A83 is the current version of the swing shot. Again, J&H built that. We tend to manually cut our parts when it's only one build, and then if we're going to build a bunch of them, we CRC laser cut them using imported code from our on-shape designs through a slicer, a 3D printer, and a G-code file to a micro SD card, and then DXF G-code file to our RD Works file for doing CRC laser cutting. And that's pretty much it. Occasionally we use MATLAB to model some of our capabilities. Most of the time we just, with rockets where we can, we use OpenRocket because it's free. Our tools are typically the engineering tools in CAD or Onshape. We'll use Simplify 3D or Idea Maker is another, and then we use just forgot the name of it, but you saw it previously, C3 or whatever that is. We have a Prusa i3 Mark II type printer, which is a form of a Monoprice 3, and it's been modified to have a automated zero-point detector. Our flight simulations are done with MATLAB, Simulink, and as I said previously, OpenRocket. Whenever we code one of our microcomputers, we typically use C++, either on a BeagleBones or we rarely use the Arduino because of its less complex development environment. So more likely we'll code on a Raspberry Pi or one of the other variants, NVIDIA, small computers. Our printed circuit board design tool is the Eagle, AutoCAD Eagle, and we'll print our own circuit boards as long as they're no more than 2 layers. And if they're more than 2 layers, we have to ship them out to China or special product prices in the U.S. if they can compete. Most of the time, our Android apps are done with Android Studio and coded up in Java. We occasionally use Python. So just walking through our recovery systems, always important. We keep a launch history of various rockets and a projection of what kind of motors we want to use in them. We always have a bill of material of the parts that we have, and then we tend to go through our configuration process, mostly for configuring the computers, autopilots, flight controllers, things like that. I'm pretty much just going to hop through this. We don't need to talk about the remote receivers, telemetry radios. We'll run this down through wireless telemetry. There's a number of tools out there, short-range tools for Bluetooth, FrSky. We tend to prefer originally using XB, but now we use the SIK radios almost exclusively, and Spectrum receivers with Spectrum transmitters, transceivers, just because we like their approach and it's simple to use interfaces. Long range wise, you have the RFD 900 and even Dragon Links, Virgin's Ubiquity Rocket M2 type long range wireless. We tend to prefer the RFD 900 series. You can connect cameras into these systems, put a camera into your rocket glider. That's not too hard to do these days. And these are drone cameras, but they'll go in the rocket ladders just fine. So that's the end of our video today, and I hope you've enjoyed it. It's just been a review of all of our boost glider and rocket glider designs that we're working on. It's basically just one project out of 97 that we have on our computer, and it takes a lot of work to get these ready for contest, and we're trying to get ready for the summertime NARAM 63, and hope we'll have a good design finished by then, and 2 or 3 test versions done. We'll show you the test videos of those as we complete them. Hope you enjoyed it, and as always, take care of yourself, and have a good day flying your rockets.